is that the halogens are on opposite sides. So that's a key characteristic of that. And it is always the case. It's always the case. Regardless of if you're using chlorine, bromine, or iodine, it's always going to be the case. They never add to the same side because the atoms are just too bulky and they don't want to be right next door to one another like that. A variation of the halogenation is, let me take this and copy it, is what we call halohydrin synthesis.
Excuse me, Dr. Russell.
Yes.
When you get a chance, may I speak with you after class? Sorry to interrupt.
Depends on what you want to ask me. No, I'm joking. Yeah, you can. You
Okay.
can actually, if you want to broach the conversation, you can actually send a private message on here, and then I'll know what to expect.
Okay, thank you.
All right. Yeah, no problem. All right, so we're gonna take this example. This is an example of halohydrin synthesis. And if you look on that overview handout, it goes through all the different characteristics. This follows the exact same mechanism as halogenation, right? But the outcome is a halo alcohol. So I'm gonna draw the product. Put that down. So this is the product, right? Notice I'm starting with Br2, right? But I'm also doing it in water. So water is actually gonna pop open the Br2 ring rather than the other bromine, right? And there's a reason for, I'll explain that, because water in this case is the solvent. Right. So that's the fact that water is the solvent, what that means is that there's a lot more water than there is bromine present, right? So if we start with, let's say, a 1 mole of bromine, but you have 50, if you do it in 50 mils of water, that's a whole lot more moles of water. And that, I'm saying that because when we get to the mechanism, you're going to see when it's time to open the ring, which this goes through the exact same mechanism as the halogenation. When it's time to open the ring, it's the water that does it. All right. So the mechanism is just like halogenation. So we're going to start out with that. So this is my Br2. So the ring is going to attack that. Well, not the ring, I'm sorry. The pi bond, the electrons in the pi bond are going to attack that and break the bromine-bromine bond. And then so you end up with this intermediate. And a plus charge here. Now, what happens here? If you recall from the halogenation reaction, what's going to happen? Is that going to stay like that? And then this is an intermediate. And I have a bromine out here. Anybody remember what happens there? The bromine doesn't attack, right? We talked about this on Friday. What happens here when you have that bromine next to that plus charge? And I gave you a term to describe it as well. Doesn't this close up? All right, so that closes up like that. Anybody know the name? Can somebody give me the name of this intermediate? All right. So this is, we left off right here. You have this bromonium ion intermediate. Right. And then, of course, bromine is still out here. The one you lost over here after you broke the bromine bond. But the water is also here. Right. And so it's actually water that comes in and opens this ring up. All right. And this is purely stoichiometry. Right. There's more water present than Br because water is the solvent. So the water is going to open the ring up, and I'm going to end up with my halohydrin. Well, not quite, but I'll end up with another intermediate. And then this is here. How do I get rid of that proton to make that an OH? Anybody?
Do you draw an arrow from Br to one of the hydrogens?
So like that?
Yes.
Mm-hmm. So I just, the last step would just be to do a proton transfer. And then that way I'll have my halohydrin plus HBr. Right. Any questions about that mechanism? It go again. The first step is just like halogenation. The only difference is how the ring gets opened up. Right. And so in this case, the ring is opened by water instead of that other bromine. Any questions about that? All right. So the other methods that's here, this is the same. This is also a halohydrin synthesis, but it's just using a different set of reagents. Right. And this is done in DMSO and water this is your solvent system. And then MBS is your bromine source. All right, so let me show you what MBS looks like. But we're not going to go through the mechanism for that. We'll just give the product. This is MBS, N-bromosuccinimide. Right, so that's where the bromine comes from for that reaction. All right, so the outcome is the same. Right, where the bromine is at one side of the alkene and the water is on the other side. All right, but that set of reagents, if you were to make a flashcard, that's what will be over your arrow. It's MBS, which is here, and then water and DMSO. Both. So DMSO is also a solvent, and DMSO is dimethyl sulfoxide. Looks like this. very polar solvent. So it's really for polar reactions. Because if you remember back when we were talking about functional groups and physical properties and chemical properties, we talked a little bit about solubility and the fact that like dissolves like. And so DMSO is polar because this reaction has polar reagents. All right. Any questions about anything? Let's work through a couple of examples on number 5. Right. And this is going to be kind of a review to jog your memory. It asks what alkene can be used to prepare each alkyl halide. Now we start out with the alkyl halide, but we're trying to get to the alkene. What is when you hear the term alkene, what does that mean? Like what is
Compound with a double bond.
you got a double bond? What have we recently looked at or recently studied? What technique have we recently studied allows you to make double bonds? Right. What type of reaction makes double bonds? I guess that's what I'm trying to get at.
Is it elimination?
Elimination. Good. Excellent. So if I wanted to take this alkyl halide back to an alkene, I'll need to eliminate H and Br, right? If you remember, if Br is my leaving group, and then my alpha hydrogens are next door, I could just simply do an E2 elimination to get me back to an alkene. Are y'all following that or no? All right. So anytime I want to go from the product of an alkene reaction back to the alkene, I just need to do an elimination. Right. So what I can do is eliminate here, and without going through all the. We'll just assume that it's E2. I can eliminate here, and that will give me this alkene. Right. And then vice versa, if I want to go back, I just add HBr to the alkene. It'll get me back to the product. So let me clean this up. All right. Questions about that? Let's do another one. Let's do this one. And let's say I wanted to get to this alkene. Where would I eliminate from to get that? Right? What do I need to look for? If I'm thinking about elimination, I need to find a leaving group. Is that right? And then all of my alpha hydrogens. So this is alpha, that's alpha, and so is that. But which one of those alpha hydrogens would give me a double bond where we have in the product? Let's write this out. So this is C. That's too thick. This is C, H, H, H. Go ahead, Mike.
What is the methyl group?
The one that I just wrote out.
Yeah.
Yeah, you could eliminate from there. That's exactly right. So I can do this and this, and that'll give me that. What if I wanted this alkene as the what if I wanted to go back to here? How would I get there from here? Because you can get either one. Which alpha site would I take a hydrogen from for that one? So I have hydrogens here, right? What would you do?
Do you take a hydrogen from the top carbon?
I do the same thing. It's
and
not something different. I would just take off a hydrogen here and then lose my leaving group. Anytime you want to eliminate to get an alkene, you always find the leaving group first. That's the strategy. Find the leaving group and then find the alpha sites, and you'll know where you can eliminate from. All right, let's go to the next page. Any questions about that? I want you to do this one on your own. Right? What would that be a product of? What if I had an alkene and I ended up with this product? What reaction would that be? What reaction would I use to make that product? If I wanted to put two bromines on and I started with the alkene, what would I use? All right, we're going to come back to that. Make your flashcards. I promise you, they'll save your life. Let's go to the next page. We're going to start working through this reaction wheel, and I'm going to just take each one of these reactions. Well, actually, we're going to do the ones that we've already covered. We'll do those first. So we know we should be able to, at this point, we should know what that's going to do and what that's going to do. So let's do those first, and then we'll go back through the other ones and talk about them. All right, so let's see, what would I get here if I took this alkene right here and I reacted it. Keep in mind, nothing else is reacting. Whenever what we're talking about now is reactions of alkenes. So all I'm focused on, all I care about is the double bond. So what is the product of taking that double bond and reacting it with HCl? Anybody. If I take HCl, I'm going to add H to one side and Cl to the other side. The question is, which side is H going to be added to? Which side is Cl going to be added to? That's the question. All right, remember this is addition of HX. It is Markovnikov regiochemistry, right? And H adds to the least substituted side, and Cl is going to add to the most substituted side. If you look at that double bond, which side is more substituted? If you look at the two carbons.
The left side.
Left side, right? This side right here. So in the product, that's where chlorine is going, and H is going to this side, to the other side. So let's draw that out. So this is, so chlorine is going to be here. H is here. Anybody not see that or not following? It's going to take some reps. That's why I'm telling you up front, make flashcards, but don't make them when we get to the end. Make them now. So you can look at them every day before you come to class, after you leave class. All right, so that reaction is addition of HX. Over here, we just did this, right? This is what? Somebody tell me what that reaction is. I got Br2 and I'm doing it in water as the solvent.
Is that halohydrin synthesis?
Halide, good. What's the outcome? Let me say this too. For halohydrin, the OH, that's going to be on the most substituted side of the alkene. If it's unsymmetrical, like this one, right? So what am I adding? I'm adding Br to one side and OH to the other side. Now, this is not the, we're not talking about the mechanism now. We're just talking about predicting the products. That's different. Predicting products is not the same as proposing a mechanism. So the question is, which side am I adding Br to? Which side am I adding OH to? If OH is going to add to the more substituted side. Because we just confirmed that the more substituted side is the side with the methyl group attached, right? So I'm going to add my OH there, and I'm going to put it on a dash. And then my Br, I'm going to put on a wedge because these two still have to be trans. Right, they still have to be opposite to one another. But anybody not following that? Or not see what happened? If you have a question, feel free to ask it. All right. Let's do this one. This is the easiest out of all the reactions we'll learn. This is the easiest one. This is hydrogenation. It's hydrogenation. The easiest of all the reactions that we're going to study. All I'm doing here, so I can shrink that down. All I'm doing here is adding a hydrogen to each side of that alkene. This is a way to make alkanes from alkenes. Or to convert alkenes into alkanes. Right? So if I'm going to add a hydrogen to each side, then my product is going to look like that. Right? Where I've added a hydrogen here and one here. So you have to do this in the presence of a platinum or a palladium catalyst. And the mechanism is it's a little bit beyond the scope of the class, but the metal itself is highly involved in that mechanism. It's like a 3-step cycle. You do insertion, you do you do a addition, migratory insertion, and then reductive elimination. None of which means anything to you at this point, but yeah, but the goal is to take, for those reagents, is to add a hydrogen to each side of the alkene. So it doesn't matter what the alkene is. If you hydrogenate it, it's going to destroy the alkene and you'll end up with the alkane. All right, any questions about that one? This one we're gonna do on a different page, so I'm just gonna copy this and I'm gonna add a page. All right, so we had this and this was my start material. All right. Now this is, I'm gonna do the opposite of this too. I think this was in that last video that I sent, but you probably hadn't watched it because you probably was preparing for the exam. So we're not gonna sweat that part. All right, this is oxymercuration. So oxymercuration and hydroboration go together because they're both, this is an alcohol synthesis method. So you're taking an alkene to an alcohol. And you do it with Markovnikov regiochemistry. All right, so let me explain that. Oxymercuration and hydroboration, they go hand in hand. They're like, this is like this reaction, even in spite of all this stuff, basically what you're doing is adding H and OH to that double bond. That's the essence of it. That's what happens. It goes through a lot of, the mechanism is quite involved and it goes through a whole lot of stuff, but the essence of the reaction is to add H to one side and OH to the other side. And the OH, because it's Markovnikov addition, is going to add to the most substituted side. Right, it adds to the most substituted side. So let's look at the outcome first, and then we're going to go back and look at the mechanism. All right, so this is the outcome. You get an alcohol, and the OH is here, and H is here. It's that simple, right? Even if you don't know the mechanism, you should be able to predict the products, but that's going to take practice and time and reps, looking over the reactions, making flashcards. If you don't want to make them, which I suggest because that's muscle memory if you write it out, but you can also download as an app in the App Store or the Play Store. I think it's called Organic Chemistry Flashcards or something like that, and it has all these reactions in it. But I suggest that you do one or the other. My preference is that you write it out though, because when you write it out, that's training your hand and your eyes and all that stuff to draw the products out. All right. So this is a way to make alcohols. The other way is, let me copy it from here, right here. Boom. The other way to make alcohols is here. I'm going to put this over here as a subheading. Right. The other way is to use hydroboration. Crop this out. Right. So so hydroboration is it's not the same reaction. It's a similar reaction, right? But the essence is the same. Add H to one side, add OH to the other side. It's the thought and the idea behind it is the same. So if I take this alkene, same alkene, I'm going to get an alcohol, but this is anti-Markovnikov. Right, anti-Markovnikov. So that means, what does that mean to you? Knowing what the regiochemistry is for the top reaction. In other words, where the OH adds and where the H adds. That's Markovnikov. What did we say that meant again? right? What that means is that the OH is going to add to the most substituted side. Yeah, I wrote it, but I'll write it again. It's fine. So if it's anti-Markovnikov, what do you think, logically, what do you think that means? Where's the OH going in this case?
To the least substituted side.
To the least substituted side. Right, so H is going to one side, OH is going to the other side. So here, my product is going to look like this now. OH is here, H is here. But the essence, again, even if you don't, because this mechanism is very involved, even if you don't know the mechanism and all the arrows, the essence is to add, basically, essentially adding water to that alkene. You add H to one side and OH to the other side. Let me copy this right here. Right, that's the essence of both of these reactions. You basically add water to the alkene, H on one side, OH on the other side. That's the way to remember it. If you watch that video, this was BAM, boron is anti-Markovnikov, and then this was, right? So oxymercuration is one, and this is, I didn't give you the name, this is hydroboration / oxidation. Two reactions to get, both of them make alcohols from alkenes, but the regiochemistry is different. Any questions about either one of those reactions? So what that little mnemonic, MEM, mercury is Markovnikov, and then BAM, boron is anti-Markovnikov. So that's how you know where to put your OH and where to put your H in each reaction. And we'll talk about the mechanism for each one as well. So let's go back up to here first and finish this, and then we'll come back and talk about the mechanism. So what's the product here? Well, it's kind of a dumb question because we already wrote it out. So the product here is going to look like this. Right? And let's do this other reaction first, and then we'll go back and do the mechanism for oxymercuration. So this right here, this reaction is what we call osmolation. These are the reagents for it. Osmium tetroxide and sodium hydrogen sulfite. Right? Those are the, when you see OSO4 and sodium hydrogen sulfite in the presence of an alkene, it does one thing, right? This is a way to make what we call diols. I'm gonna put here CN diols, right? So with the osmium tetroxide and sodium hydrogen sulfite, you're going to add an OH to each side. Right, you're going to add an OH to each side of that alkene. I think we talked about this earlier. This and all these, the osmolation, oxymercuration, and hydroboration all fall in that category of ways to oxidize, which when we opened up, I kind of classified it as oxidation, halogenation, and then that was one other class that I'm drawing a blank though. that we talked about. But this is the outcome. And I'll talk about the CHEM part. I'll write this methyl group in so you can see that. So if you notice here, the alcohols are both wedged. They both are coming out of the page. That's what that means when we say CHEM. It means same side. I can draw it this way, or I can draw them this way, going back into the page on a dash line. And then the methyl group would be wedged like that. Either way, but sin, that term, sin is a way to describe what we call stereochemistry or 3D orientation. Right? It describes the stereochemistry of your alcohol. So they're either both on a wedge coming out of the page or both on a dash going back into the page. But are y'all okay with that? Anybody and not catching that when I say stereochemistry? It's a way to describe the 3D orientation of a molecule. So 3D orientation is, it could be sin, or if they're on opposite sides, it's anti. But I don't want to get too deep in the weeds on that. All right, any questions about anything so far? So again, now you got 1, 2, 3, 4, 5 reactions that you can make flashcards for. Really 6, because we did hydroboration oxidation as well. No questions. Okay. I said we would look at the mechanism for, let's do oxymercuration first, since we started with that. All right, so for that mechanism, let's just keep that start material. We got 5 minutes left. So we're gonna start with that. Again, in all of these reactions, so you have mercury, and all of these reactions, the alkene is going to be the nucleophile. Right, so this is adding here, like so, right? And then you're going to kick off one of the acetate groups. We're going to put a plus charge here. We're going to put mercury here. So we get this intermediate. Uh-oh. Right, and when we lose that acetate group, let me give you that too. It's just kind of hanging out here for now. Right, so mercury can actually cyclize here. right? So this is going to cyclize, and you get another intermediate that looks like this. So Hg, OAC, and now this is positive. Boom. So that first step is going to look like this. Have you noticed how it's written? It's written in stages. So the one up here in front of the mercury acetate and water, this is what happens first. And then once we get to the outcome of that reaction, then the second step is going to happen on whatever the product is of that reaction. Right. So here I have OAC minus, which doesn't do anything yet, but I also have water. All right. And so now it's water that's going to come in and pop that intermediate open. This is a mercurinium ion. Water is going to come in and pop that open. And again, this is all, if you have a grasp of nucleophiles and electrophiles, that's all this is. Everything is one or the other. In this case, the water is the nucleophile. And then this is my electrophile. So water is going to attack this carbon right here and pop that ring open. And we've seen this before. It's just like the halogenation intermediate. It's the same like the halohydrin that we just did. All right, so now we end up here. Let me just draw that out. So now this is HgOAC, and then this is OHH. That CH3 is still there. Let me give it some stereochemistry. And this is that CH3. So this is positive. It's also intermediate. What can I do to make that what can I do to get that water to become an OH? Anybody? I have this OAC hanging out here. It's not a great base, but it's a decent base. What can I do? I want to get rid of one of these hydrogens. And I have this OAC down here that can help me do that. What would you do? If this is the base, again, nucleophile, electrophile chemistry, acid-base chemistry. That's the base. This is the acid. What would you do if you wanted to pull off that proton? Can you do a proton transfer like this? So you'll end up with this as the final product of that first step. That's OH, HgOAC plus, right? This is the proton that got pulled off. And I need to put that methyl group back in. Right, so this is the product of that. Right, and that last step, that NaBH4, that's the second step. Right, I'm just going to replace mercury with hydrogen. Right, so that final product is going to look like this. This is step 2. right? So again, it's the same. It's added H, add OH. OH goes to the more substituted side. H goes to the least substituted side. That's the oversimplified version, but the mechanism itself is a little bit more complicated. All right, so we're going to stop there because I'm 2 minutes over. Any questions about anything?